So let me remind you where we are now. We're talking about probability and statistics of common substrings and related things. So length of longest common substring. And let me remind you again why we're doing this. Why are we spending so much time and effort trying to understand the probability of these things and the statistics of these things? It's because when you do a match between two sequences, and even more so when you do a database search, we have one sequence and you're going to align it to a whole bunch of sequences, and you come back with the best alignment that you found. And you stare at that thing and you ask yourself, does this alignment mean anything biologically, or is it just something I might have expected, even if these two sequences are random, even if they have no biological connection whatsoever? You need something concrete to be able to compare against. You need some theorems of this type. Otherwise, you're just staring at all these characters. And I, for example, have no good intuition if I just stare at two alignments, unless they're really horrible or they're absolutely identical or nearly so. But in the middle, I don't really have any good intuition as to whether what I'm looking at is just random phenomenon or not. And so you need some absolute guidelines to help you there. And these kind of guidelines are built into most of the database searching programs today. When we get to BLAST, we'll see that very definitely. The specific things that we'll be analyzing are simpler than what comes up in BLAST. But if we develop some facility on the simple problems, it'll help us at least to understand, absorb the results without deriving them, but understand the results that come up in more complex situations. So here we are. We have two random sequences, each of length n. I'm just going to assume for simplicity that they're both the same length. And the actual characters, or the character at any position, is picked randomly uniformly from an alphabet of size z. Okay, so z characters. So the probability of picking any specific character, any given character, is of course just 1 over z. Okay. So, let's say this is just DNA, and I randomly flip a coin, and there's an A, and I flip another coin, there's C, there's an A, C, C, T, A, G, G. That's probably not very random, but I was pretending I was flipping a coin, so that's as close as it's going to get. And then I have, T, C, A, C, G, G, T, T, A, and is there a common substring longer? Oh, look at that. I did this one without paying attention to this at all. And here's one. Now, of course, this is in the same position. That's purely coincidental. It doesn't have to be in the same position to be a common substring. Do we see another common substring other than just a single character? I don't see one. But just for illustration, AAT, and suppose we had a CTA, and here would be a common substring with that one. So just to illustrate the fact that they don't have to be in the same position. The longest is length 3, and we're actually seeing in this example it comes up twice. I could have cooked up a different example. All right. Last time I reminded you that if we were talking about subsequence, then the expected length of the longest common subsequence in DNA 4 is about a half, or that's known to be more than a half n. And what was established in class a week ago was that it's at least a quarter n. So that's a pretty big percentage of the sequence, which means if you're measuring the similarity of two sequences by the length of the longest common subsequence, it better be pretty long. It's got to be a lot more than half to impress you that it's anything other than some random type phenomenon. Of course, we're still just talking about expectation and not the actual probability distribution, but still, the expected value gives you some indication of the fact that because the expected value is big, you'd better see something bigger than that to be terribly impressed. Okay, last time we argued that the expected length of the longest common substring is going to be less than or equal to the expected length of the longest common subsequence. Because for any actual two sequences you give me, two strings you give me, a substring is a subsequence. So the longest common substring is certainly a candidate for the longest common subsequence. And there may be subsequences that are common subsequences that are longer. So whenever you average over the length of the longest common subsequences that you find, that will be greater than or equal than, in every case, it'll be greater than or equal to what you get for the length of the longest common substring. Let me just give an illustration here. What's a common subsequence here? Well, maybe it's this A with this A, this C with this C, and where do we get? Maybe this T with this T, this A with this A, and then there we go. So there's a common subsequence of length 1, 2, 3, 4, 5, okay, which is bigger than 3. All right, so we're going to analyze the expected length of the longest common substring. All right. Now, the first observation is this. If here are my two sequences. I pick a position I here and a position j there. Okay, so two fixed positions. Okay. Pick two fixed positions. What is the probability that starting at I in the first sequence and starting at j in the second sequence and j in S2, the two substrings match for m characters. Okay? So let's say here we have an A. They match. And there's another one. Another one matches TG. Mismatch. Okay? But as a function of m, what's the probability that they match for m at least? I'm not asking whether they match beyond m. What's the answer to that? Well, if they're going to match for m, they have to match for the first one, assuming m is bigger than 0. The first one has to match. What's the probability of that? Remember how these things are generated. This is probability P. 1/4? Sorry, say again? Well, okay, I'm doing this in terms of P and Z. So these are... one over Z, which is known as, which I'm calling P. Yeah, I mean, the probability that these two characters will match, this is something. It doesn't matter what it is. Then the probability that this one down here is equal to that, matches that, is just P, or 1 over Z. This is picked uniformly over an alphabet of size z. So the probability that this is the same as that, no matter what that is 1 over z, but we're calling that p. It's important to see that it's p and not p squared. Sometimes people think it should be p squared. The probability that this is an a up there is p, and the probability that this is an a down there is p. Multiply them together, it's p squared. That's the wrong thinking. If you want to do that, then you have to say, what was the probability? You have to add over all the possibilities of what's up here, not just a, but t, c, and g. Okay? But the better way of thinking of it is, this is going to be something, doesn't matter what it is, then the probability that this is the same as that is just 1 over z, which is p. So the probability that this matches is probability p of matching one position. Okay. Well, if that matches, what's the probability that the next one matches? Yes, that's also p independent of the first one, because we picked, the way we picked these sequences, each position was picked independently. So that's the probability of p the next time. So what's the probability that you have m matches? It's p times p times p m times, so it's p to the m. So p to the m. Okay? P raised to the m. Now, they may match for more than m. This is not saying that they match for exactly m. If I was to say that they're going to exactly match for m, then the next one would be a mismatch, which happens with probability 1 minus p. Yeah?
Do we need to consider not only the match, but also the position? How they match the position?
The question is, do we have to consider the position? No, I've already restricted the problem to say that we're starting at I and we're starting at j. So the positions are known, okay? And then I'm asking, going forward from those two positions, what's the probability that they match for m? Now, you probably asked that question because in the expected length of the longest common substring, the starting positions could be anywhere, and we're going to bring that into the analysis. But right now, we're just looking at a simpler issue. If I tell you that one begins at I and one begins at j, what's the probability that going from those two positions, they match for m places is just p to the m. Okay? So that's a fact we need to know. All right. The next step of this analysis, so that's just, I'll call that fact 1. So the next step in the analysis is I'm going to let xijm be a random variable with value 1 if starting at position I and starting at position j at positions I and j, there is a match of length m. Okay? And it's 0 otherwise. This is, I'm just saying, if you look at two sequences and you look at position I and position j, and there's a match of length m, then this random variable will take a value 1, and otherwise it'll take a value 0. Now, I'm assuming, well, it's part of the prerequisites that everybody here has had a probability and statistics course. One thing you may not have really absorbed is the terminology random variable. Okay, but random variable is just a variable whose value takes on a value according to some probability distribution, probability scheme. So, well, we don't necessarily know what it is, although actually we just worked it out, didn't we? So xijm is going to take on a value of 1 with this probability, p to the m, and it takes on a value 0 with 1 minus p to the m. Okay? All right. So now consider this thing. Cm is defined as the summation I equals 1 through n, j equals 1 through n, of x, ij, m. Who can parse that? What is this actually saying? This is the definition. Cm, I'm just going to call that. But what is this thing actually counting?
All the matches that from the beginning to match all of them.
Counting all the matches, close, but not quite. These double summations were considering all possible combinations of I and j. And for each one, we have this random variable, which is either a 0 or a 1. It's a 1 if starting at position ij, there's a match of length m. And it's a 0 otherwise. So who can put into words what this really means? I know we have a whole bunch of statistics graduate students here, all looking at their shoes. Yeah.
Starting from the first position for the I and first position for the j, we're trying to match the strings, and if there's a match, we put 1, and if there's a mismatch, we put 1 minus p. X, I, j, m value will be p to the m for matches and 1 minus p for each match.
Well, now, p to the m is the probability that this is 1. We're not into the probability yet. Just this is either a 1 or a 0. You're getting close. I mean, again, we're counting over all possible combinations of I and j. But any other takers? Yeah. Yeah, okay, so it's the total number. So the interpretation is this is equal to the total number of pairs of starting positions of matches of length m. So a more abbreviated way of saying that perhaps is it's the total number of matches of length m. Okay, and you could have a match of length m starting at one position 5, say, in one string, and 7 of the other one, and then again 5 and 26. So the same I could be used several times. The same j can be used several times. So if we go back over to this example, so in this example, for m equals 3, then I think Cm equals what? I think it's 2. I think there are only two places, two pairs, where we're seeing matches of length 3. It's these two starting positions and these two starting positions. If we go to 2, then we're really, we'd have to take some time to actually look at this thing closely, but there are lots of them. You'd see this one is a pair, this is a pair, CC, I guess we don't have a CC in there. We'd have a AC, AC, lots of them. Okay, so Cm, I don't know what it is. It's certainly bigger than 2. But you can try to work out that example if you like. Okay, so I'm interested in at this point in the analysis, we want to study or understand ECM. Okay? What is the expected number? What is the expected value of CM? What's the average if you took a lot of random sequences? Implied in here, by the way, is that they're all of length n. and they're generated the way I've said. So I'm not putting in here the fact that they're length n, and I'm not putting in the p. That'll, of course, come up in the formula. But I'm interested in you generate two random sequences of length n, and you figure out what Cm is. Another 2 Cm. You just do that forever, and you take the average over all those. That's the expected number, expected value of Cm. Okay, so what is that? Well, it's always a good idea, if you don't just immediately see the answer, to write out the definitions again. So we have Cm defined over there. It's the expected value of this double summation, I equals 1 through n, j equals 1 through n, xij m. Okay? All right. Well, something that came up, I know, in lecture a week ago, and a very important thing to remember from your elementary statistics class, probability class, is what's called the linearity of expectation. Whenever you take the expectation of a sum, and here we're taking a sum of many random variables, that's the same thing as the sum of the expected value. Okay? So this is just equal to double summation xij_m. I equals 1, j equals 1 through m. What's n? Okay? That's linearity of expectation. Don't try this with variance. Okay? It's not generally true with variance, although it's true in case these are independent. All right. Now, what's expected value of xij_m? Again, when you're stuck, if you don't just immediately see the answer, write out the definition. What's the definition of expected value?
For variables?
Well, it's going to be, I'll tell you, in general, but for this particular problem, it is xij is equal to, you have to consider the two possible values of xij, xij_m. What are the two possible values? What values can xij_m take on? 1 or 0. So this takes on 0 with some probability. Actually, hardly matters because it's going to be multiplied by 0. But just to see anyway, what's the probability that it takes on the value 0? Well, let me actually do it the other way around because then it'll. It takes on the value 1 with what probability?
P to the m?
P to the m. Okay, that's really what we did. We didn't call it that, but that's really what we did over here. We said the probability of xij_m was p to the m, the probability it matches for m positions. So 1 times p to the m, and then you have to consider the other possibilities. Well, in this case, it's just 0, 1 minus p to the m. But as I mentioned earlier, you're going to multiply by 0 anyway, so it doesn't matter. So this is p to the m. Hmm?
1 minus p 14 to the n.
What's the question?
There is nothing matching there, right?
Well, no, the 0 is what you get. It's the value you get from the random variable xij_m when there is not m, when there aren't m matches. But there might be, I don't know, m minus 6 matches or something. But there aren't m. So this is the probability that there are m matches or more. But this is the probability that something other than, something less than m. Okay, so that's p to the m. So we know what that is. All right. So expected value, therefore, of Cm is equal to this double sum, I equals 1 through n, j equals 1 through n, of p to the m is equal to, just checking, well, all right. I'm going to n squared p to the m. What's really wrong? I did a little bit of cheating here. Yeah, because if m is big, you can't. See, I did the sum over all ij positions, but if n is anything bigger than 1, you can't cram at the end a match of length m if one of those starting positions is closer than m characters away. So I really should have accounted for that up in here. But for n much bigger than m, and that's what's of interest here, this is right. So really, where was the approximation? The approximation was somewhere in there. Okay. Hopefully everybody understands what I just was mumbling. If you want to do this absolutely right, you have to make these endpoints different than n, because you simply can't put a substring in here of length m if it's starting, let's say if m is 5 and you're going to start one position from the end, there's just no room. Okay? But if n is really big, and m is compared to m, the exact amount here isn't going to be much different than that. So it's about n squared m. Okay. So now we know what the expected value Cm is. It's about n squared m. Now, the thing I want to point out is how does the expected value of Cm behave as m increases? So we fix n. N is 10 million, whatever, million, whatever. P is a quarter, 1/20th, something. Those are fixed numbers. But now m is how many matches we're going to have. And initially, if m is 1, then we know that's p. And the expected, the first match is probably p. The next one is p squared. But here's the expected Cm. How does that behave as m increases?
Well, p is definitely a number smaller than 1, and power of p will decrease, will approach to 0 as we go.
Yeah, it falls as m increases, okay? So this falls as m increases. And does it fall slowly?
It's going to go fast.
It falls very quickly. So, it's not unusual that you'll have a match of length 1 somewhere, or that there's the ECM when m is 1, that expected value is pretty high. When you get to 2, the expected number of matches of length 2 is less, and the expected number of matches of length 3 is even less, and it just starts going down very quickly. Okay? So this drops very quickly because m is in the exponent. P is less than 1, and unless the alphabet is only a single character. But for alphabets of size larger than 1, this P is less than 1, and this product, as we multiply more and more P's, it decreases very rapidly. Okay.